Today, we're going to tackle a puzzle that's so tricky, it can bring even the most powerful computers to their knees. But we're also going to look at this really clever, nature-inspired algorithm that actually figured out how to solve it. Okay, I know this sounds like a weird one, right? What on earth could putting together IKEA furniture have in common with designing the super complex microchips that power your phone? Well, the answer, and you've probably guessed it, is that the order of the steps is everything. I mean, get the sequence right, and you've got a perfectly good piece of furniture. But get it wrong? Well, we've all been there. You end up with a pile of spare parts and a massive headache. And this points to a really fundamental truth for pretty much any complex system. It's never just about having the right pieces, it's about putting them together in the right order. And when you're talking about something like designing computer chips, getting that order right isn't just a nice to have. It's literally the difference between a working piece of tech and $1 billion paperweight. Okay, so let's get specific here. The actual puzzle we're diving into is called the BDD reordering puzzle. And believe me, this isn't just some academic exercise. It's a high-stakes challenge that engineers and computer scientists deal with all the time. So, what in the world is a BDD? Well, a binary decision diagram, you can think of it as a super compact, super efficient flowchart for logic problems. It's a way for computers to map out decisions. And these things are everywhere. They are the unsung heroes working behind the scenes in AI, in chip design, pretty much all the modern tech we use every day. And this right here gets to the absolute heart of the problem. What you're looking at are two diagrams for the exact same logic puzzle. The only difference? The order of the variables. On the left, with a good order, it's clean, simple, compact. But on the right, it's a total tangled mess. The whole game is trying to find that magic sequence that gives you the nice, clean diagram on the left. So you might be thinking, why not just find the best order every time? Well, here's the catch. Finding that perfect sequence is what's known in computer science as an NP-complete problem. Now, that's basically just code for impossibly ridiculously hard. We're talking about a problem where you can't just brute force it and check every single combination. Why? Because you'd be dealing with more possibilities than there are atoms in the known universe. So yeah, you need a much, much smarter way to do it. And that smarter approach? Well, it comes from a pretty surprising place, Mother Nature. So let's talk about how we can crack this thing using a concept called digital evolution. This is where the genetic algorithm comes in. It's a really cool problem-solving method that's basically inspired by natural selection. So instead of trying one single answer, you start with a whole population of possible answers. In our case, a bunch of different variable orders. Then you just let them evolve over many generations. The best ones survive, and you combine them to hopefully create even better solutions. One of the key tools for this is something called crossover. You can literally think of it as digital breeding. You take two pretty good parent solutions, you mix their best parts together, and you create a new offspring solution. And the hope is, of course, that the new one inherits the best traits from both parents. And the other big tool is mutation. Again, just like in biology, this is all about introducing small, random changes. So for a puzzle, that might mean just swapping the positions of two variables. This is so important because it stops the algorithm from getting stuck in a rut. It forces it to explore brand new possibilities that it never would have found otherwise. Okay, so we've got this awesome nature-inspired tool. Sounds like we're done. Problem solved, right? Well, not quite. Turns out the standard genetic algorithm has a hidden trap, a fundamental flaw that we have to figure out how to get around. And that trap is a classic trade-off, one that comes up all the time. It's exploitation versus exploration. So exploitation is all about digging deeper into the good solutions you've already found, making them even better. Exploration is about searching for brand new, maybe even totally different solutions. And you've got to get the balance right. Lean too hard on one, and you either get stuck with a good enough answer, or you just wander around forever and never actually land on a great one. This leads to what the researchers call the homogeneity trap. Basically, as the algorithm keeps running, all the good solutions start to look really similar to each other. The population becomes homogeneous. And when that happens, crossover doesn't really create anything new anymore. And the whole system gets stuck on what's called a local minima. I love this analogy. It's like you're climbing hills in a thick fog. You get to the top of one small hill and you think, great, I made it. But you can't see that the real mountain peak is still way off in the distance. The algorithm finds a good solution, but it misses the absolute best one because it stops exploring too soon. So, how do you escape that trap? This is where the paper gets really cool. The researchers came up with this incredibly elegant solution. They built an algorithm that can adapt. You could almost say it's an algorithm that becomes self-aware. And the logic behind it is actually brilliantly simple. At every single step, every generation, the algorithm actually stops and measures the diversity of its own solutions. It's asking itself, hey, are all my ideas starting to look the same? If the answer is yes, if diversity has dropped too low, it says, okay, time to shake things up, and it forces itself to use mutation to explore new ground. But if diversity is still high, it says, all right, we've got some good ideas here, let's refine them. And it sticks with crossover. It's constantly dynamically balancing exploration and exploitation all by itself. So the big question, did it actually work? Oh yeah, big time. Just look at this chart from the study. That bar on the far left, that's our new adaptive algorithm. And as you can see, it consistently found better solutions, which means smaller, more efficient BDDs than the other methods. It beat algorithms that just stuck to one strategy, or even ones that tried to mix them randomly. That little bit of self-awareness made all the difference. Okay, so this is an amazing solution for a very specific, pretty nerdy computer science puzzle. But let's zoom out. What's the bigger picture here? What's the main takeaway for the rest of us? The really big idea here is the power of finding an intelligent balance. See, the best way to solve any hard problem is knowing when to double down on what's already working and when to go out and explore for brand new ideas. What this research shows is that we can actually design smarter algorithms that can check their own work and switch up their strategy on the fly. And, this isn't just for computers. Think about a business trying to decide whether to improve its best-selling product or invent something totally new. That's the exact same trade-off. This idea of balancing refinement with bold innovation, it applies to just about everything. And that leaves us with a really fascinating question to think about. We just saw how this adaptive approach was able to crack the BDD puzzle. But what's next? I mean, what other huge, complex problems out there, in medicine, in finance, in logistics, are just sitting there, waiting for an algorithm that's smart enough to learn how to change its own mind?